All right, good morning, everyone. I'm Sean Bennett. I'm the research librarian here at NC State, or rather one of them. And I'm so pleased to welcome you to today's Coffee and Viz on modeling Jupiter's Great Red Spot. So a few housekeeping things before we start. There will be a Q&A at the end of our talk, so please hold your questions until then. And on the topic of Q&A, we do have some library community guidelines to go over. The libraries and its partners are working to ensure that our programs are welcoming and affirming for everyone involved. This means that everyone, including organizers and attendees, has an important role to play in contributing to that respectful and positive environment. That's why we ask you to reflect on the way you pose comments and questions today to ensure they don't harm other participants. The impact of our words is really just as important as our intent. Today, we ask that you engage with this program with exploration and curiosity, while being kind and intentional with your words for the sake of our community. If this is your first time at a Coffee and Viz, welcome. This is a libraries-run program that gives a chance for researchers across campus to come and talk about really cool stuff. It's an ongoing program. It's free and open to the public, so check out our schedule. I think we have at least 3 more scheduled for this semester. So we're fortunate enough to have 2 speakers with us today. Our first is Caleb Keaveney, a senior undergraduate student at NC State studying meteorology and applied mathematics. A Goldwater Scholar, astronaut scholar, and a recipient of the NC State Space Grant, Caleb is an accomplished undergraduate researcher interested in planetary meteorology. He spent 2 summers as a research fellow for the Juno mission at NASA's Jet Propulsion Laboratory, advancing groundbreaking research on Jupiter's high-altitude clouds and hazes, with an international team of collaborators at NASA, the European Space Agency, and in the amateur astronomy community. Our second speaker today is Dr. Gary Lackmann, a professor here at NC State in the Marine, Earth, and Atmospheric Sciences Department. His research focuses on high-impact synoptic, mesoscale, and tropical weather systems, and how these systems are affected by climate change. Gary earned his BS and MS degrees from the University of Washington and a PhD from SUNY Albany. He's been honored with the NC State Outstanding Teacher Award and the AMS Edward N. Loren Teaching Excellence Award. Please join me in welcoming our speakers today.
Morning. Thanks for being here, and thanks for that nice introduction, Sean. It's great to be back at Coffee and Viz in person after a couple of years off. I just wanted to give a brief introduction. This is really Caleb's show. I'm sort of along as supporting cast member, but about 2 years ago, I received an email from a sophomore undergraduate math and meteorology major saying, I'm interested in jets and storms on Jupiter. Would you be interested in working with me on that? Well, I study storms, and I don't know that much about Jupiter, but I'm sure I would learn something in the process as well. And so I agreed to do that. Of course, that was during the lockdown, and then we had, Caleb's a busy guy with a pretty intense double major and going out to JPL all summer every year. But we managed to carve out time to work on this. And my objectives for Jacob in being a faculty mentor were to give him experience with kind of reading the scientific literature and developing numerical modeling experiments, and analyzing the data to try to understand some of the mysteries of the largest and longest lived storm in the known universe. So I'll speak up at a couple points, but mostly this is Caleb's hard work, so I'll turn it over.
All right, can everyone hear me? All right, cool. So we're going to talk a lot about Jupiter today, but to start off with, we'll take advantage of this really cool space we're in and zoom out a little bit. So first of all, that's our sun. It's a fairly normal star, a star being any object that fuses hydrogen into helium. It's fairly unremarkable. It's larger than average, but not abnormally so. What makes it unique is the fact that we're here. It's the only star we know of that currently supports life. So that's less my expertise. The planets are more my expertise. So that's Mercury. Mercury is the smallest planet in the solar system. It's smaller than a couple of moons, actually. It's very small. And because it's so small, it doesn't really have an atmosphere, which to me as a meteorologist is kind of disappointing. The next one is Venus. Venus is the hottest planet in the solar system, which is counterintuitive because it's not the closest to the sun, but it has like a 95% carbon dioxide atmosphere, and its atmosphere is very thick. So the greenhouse effect is extremely intense. So you could melt lead at the surface of Venus. It is the temperature of a self-cleaning oven. Venus is a terrible place, but it is cool from a meteorological perspective. Then there's Earth. Earth is the biggest of the rocky planets. Earth is great because we live here. It is the only place so far that we can live. We'll see if that changes in the next 20, 30 years, but Earth is a great place. And it has a really interesting atmosphere, which is why people like us can get degrees in meteorology. Then there's Mars. Mars is not that interesting to me because it doesn't have that dynamic of an atmosphere. It used to have a more interesting atmosphere, which is why we think it used to maybe support life, but that atmosphere has since escaped. Then there's Jupiter. I won't talk too much about Jupiter right now because that's what this whole thing is about. But Jupiter is the biggest planet in the solar system by far. It's not even close. It's 2.5 times the mass of all the other planets combined. All the other planets could fit inside of it except for Saturn's rings. And these are Saturn's rings. So Jupiter and Saturn are both gas giants, very much hydrogen and helium, almost entirely hydrogen, some helium. Saturn is very low density, which makes it really interesting. So Saturn could float in water if you had a bathtub big enough to fit it in. And of course, it's most known for its rings, which are mostly made of water, actually. And they themselves have an atmosphere. It's very thin, but there's enough gravity in those rings to hold on to some gas. Then there's Uranus. Uranus is the first of the 2 ice giants. We have been to Uranus one time with Voyager 2. That's where that image comes from. Uranus is knocked on its side. So imagine if our North Pole pointed at the sun. That's kind of what Uranus is like. And all of its rings and all of its moons orbit vertically from our perspective, which makes it really unique. And then there's Neptune, which is the second of the 2 ice giants. They're called ice giants because they have a higher presence of heavier elements that we call ices. They're still mostly hydrogen and helium, but those 2 are kind of the next frontier in terms of planetary atmospheres, because we have only been there once and we are hoping to go back soon. And then, because I know some of you would be mad at me if I didn't, I've included Pluto. Pluto is a great place. I love Pluto very much, and Pluto loves us back too. That is a heart-shaped glacier on Pluto that we observed with the New Horizons spacecraft. It is a nitrogen ice glacier. And what's really interesting about that glacier is during the daytime that some of that nitrogen evaporates and, or I should say sublimates from solid to gas. And it forms a little bit of an atmosphere. And then when it becomes night again, that gas deposits onto the surface. So that part very literally beats every day, releasing gas and then having it come back down. So very cool. This is not to scale. I included it in this way because just to emphasize that these are all images. None of these are art pieces. We have been to all these places and taken pictures of them. So we have really cool observations of all of them, but we can look at it to scale. This is what it looks like to scale by the radius of the planets, with Jupiter, of course, being the biggest and Saturn close behind. And then Uranus and Neptune, still big, but not very much. And then some of these you can't really even see. And then if we do it by distance, this is what it looks like. So you can see we have lost 3, or if you're a fan of Pluto, 4 of our planets. This is where they are. Saturn is 40 feet out the door, so somewhere else in the library. Uranus is outside of the library, knocking on the front door. Neptune is having a picnic in the quad, and then Pluto is somewhere off in the trees. So if you think about this distance compared to those distances, the solar system is huge, which is why this stuff is so fascinating. So that's our solar system in general, and now we'll focus in a little bit more on Jupiter. So a little bit of history. So this is an image that I took through my telescope of Jupiter. So this little bright thing here is Jupiter, and then these four smaller dots around it are these moons, Europa, Io, Callisto, and Ganymede. And so back in 1610, Galileo was the first person to look at Jupiter through a telescope, and he saw Jupiter, this bright spot, and these four moons. And he was the first one to discover these moons, which is why now they're called the Galilean moons. And it was actually these moons that convinced him that we are not the center of the universe, that we are orbiting other things, because he saw these four moons moving around Jupiter. And so that was the first time we ever looked at Jupiter through a telescope, but he didn't really see a whole lot going on actually on Jupiter. That would come later. In the late 1600s, Giovanni Cassini observed, he made these drawings of his observations through a telescope. And the big thing here, you can see, he noted this spot. South is up in these drawings, by the way, just because of the way telescopes work. A lot of times you see south up. But he saw this really dark spot in Jupiter's southern hemisphere. And for those of you who know about the Great Red Spot, you might be wondering, is that the Great Red Spot? And the answer is we don't know, because Isaac Newton came along in the late 1600s and early 1700s, and he developed his laws of gravitation. And for the next 150 years, nobody thought about what the planets looked like. They just thought about how the planets moved. And so nobody really looked very closely at Jupiter for the next 150 years. But then in the late 1800s, we got the first photograph of Jupiter. And pictures are really hard to take of Jupiter for a lot of different reasons. It rotates very quickly, so it's hard to get a long exposure without blurring. And there's some limb darkening effects too. But you can see this very dark spot in the southern hemisphere, and that is the Great Red Spot. And the reason we know that's the Great Red Spot is because from that day forward, scientists decided never again would Jupiter go unobserved. And so basically every day since then, somebody has looked at Jupiter and tracked what it looked like. And so we know for a fact that that is the Great Red Spot. So it's at least 150 years old. Could be older. I like to think it's older, but we don't really know. So that was the first photograph, but photographs are hard to take of Jupiter. And so for a long time, what people did, even with photographic technology, was they drew Jupiter. So this is a drawing from one of my colleagues in the UK, John Rogers, from 1976. And he did a full 10-hour observation of Jupiter, the entire rotation of the planet, and he drew what he saw. And so this is how people would observe Jupiter for a long time. And you can see the detail here. We're very much indebted to people who did this, because this stuff is just really cool to look at. And there's some cool meteorology in there too. But then in the late 1900s, we started sending spacecraft. So the first one to ever go to Jupiter was Pioneer 10 and Pioneer 11 in 1973 and 74. They flew by in the polar trajectory, which means they flew, I believe it was under the South Pole. It could have been over the North Pole. It was one of those two. And so that's how we got our first observations of the poles, because Jupiter isn't tilted very much relative to us. So we never saw the poles very well. But we got some polar data from Pioneer. And then the one that a lot of people know about is Voyager 1 and 2, because these went to all of the giant planets. Voyager 1 went to Jupiter and Saturn. Voyager 2 went to all four. And we got some really good images and scientific data that we'll see later on. So that was a really cool mission. It was JPL mission too, so that's exciting. The next one was Galileo. This is the first satellite that we sent to orbit Jupiter. And so it orbited in an equatorial fashion. This is one of the only things on this presentation that's not an image. This is an artwork. Galileo took some good pictures, particularly of the moons, but not so many of Jupiter. But it did get some really good data about Jupiter. It actually dropped a probe inside of Jupiter's atmosphere, and then it burned up eventually. And that's how we got any data about the vertical structure of Jupiter's atmosphere. It turns out some of it was unique to where it dropped in and not very generalizable to the rest of the atmosphere, but still some really good data. The next one to visit was Cassini. Cassini visited in 2000 on its way to Jupiter. Cassini was or on its way to Saturn, I should say. The image of Saturn before with the beautiful rings, that was the last image that Cassini took before it flew into Saturn for its death in 2015. But Cassini was a really interesting mission for Saturn, and it took some cool pictures of Jupiter too. And then now we enter the Caleb era. This is where observations continue and become useful for what I do. So the Hubble Space Telescope launched in 1990, and it has been doing observations primarily of the really deep universe, really far away for a long time. But particularly in the last 10 years or so, they pointed it more at the outer planets as a way to get more observations of those bodies. And so Hubble has been doing basically yearly observations of Jupiter for a little while. So some of that data is really good for us. And then my favorite mission, Juno. Juno is what got me into planetary science. So in 2016, when Juno arrived at Jupiter and it sent back its images, I saw them online and they were so striking that I decided that this is what I wanted to do. And part of what makes Juno unique is its polar orbit. So this is a simulation I did in an open source software called OpenSpace, which I did an internship on a couple of years ago. And you can see Juno has a highly elliptical orbit, meaning it starts really far away and gets super close into the cloud tops, and then it shoots back out. So we get these really good observations, first of all, of the poles, but then also we can get really in close to the clouds, which is great for some more specific observations. And as was mentioned before, I worked on Juno the last 2 summers. So that's also why it's my favorite, is it has jump-started my eventual career. So yeah, and then big in the news recently is the James Webb Space Telescope, which is designed like Hubble primarily for deep space observations, but has actually turned out to be pretty useful for Jupiter. They pointed it at Jupiter a little while ago, and this image was processed by a citizen scientist in California. And it's just beautiful. You can see the red spot is really bright, and so is the equatorial zone, which is indicative of high level haze. And then you can also see up in orange here, those are Jupiter's equivalent of the northern lights, and then the southern lights too. And then you can also see in this image, Jupiter does have rings. They aren't particularly visible, but they're there. So that is the timeline of Jupiter observations and Jupiter research. And you can see the progression of our observations have gotten better over the last 400 years to an impressive degree. And this is what makes what we do possible. It would not be without first of all, the amateur astronomers who did observations like this, and then also the professionals at NASA and ESA who send spacecraft to Jupiter. We wouldn't be able to do this without those people. So.
Yeah, switch it up here a little bit. And by the way, I'm battling a little bit of laryngitis, but multiple COVID tests show that it's not COVID, for the record. I just wanted to talk a little bit about, as a meteorologist here on Earth, how does Jupiter's weather relate to Earth's weather? We have to talk a little bit about the basics. The main point of kind of the planetary basics over here is that Jupiter it's very large, but it rotates very fast. And as an atmospheric scientist, that's significant because that means the equations are easy. That means we can apply a certain set of equations that are simplified that make the dynamics really easy to understand. The same equations work really well in mid-latitudes of Earth and in the oceans, but on Jupiter, they work really well because it's rotating more than twice as fast as Earth. As far as the atmospheric composition goes, it's almost entirely hydrogen and helium, but there are trace amounts of methane, water vapor, ammonia, and other compounds. The other thing that makes it a really interesting laboratory to study atmospheric dynamics is the fact that the atmosphere is at least 3,000 kilometers deep. So there's no surface friction, no topography or the interfaces to worry about. So it's just a rapidly spinning, very deep atmosphere that's mostly made of hydrogen and helium. The cloud layer that you see in pictures like this is about 50 kilometers deep, and the clouds themselves are mostly composed of ammonia, but in the lower levels, it's thought that there's water clouds as well. And the spacecraft that Caleb had mentioned have observed lightning on numerous occasions. So we know that there's convection happening and charge separation. This time lapse here, this is from Keaveney. It shows a bit about the atmospheric circulation, but where we come in. The orange and red colors are believed to be the result of upwelled materials from deeper down in Jupiter's atmosphere. When they're exposed to ultraviolet radiation from the sun, that's what gives them their reddish color. And the term for the white bands are zones, and the dark bands are belts. And the sense of the rotation of the flow due to the shear from these jets is like a high pressure system in the bands and like a low pressure system in the belts. And then the jet streams are located along the boundaries of the belts and the zones. And the features like the Great Red Spot, they rotate in the same sense as the band in which they reside. So that's a little bit about the Jovian atmosphere. And I think now it's got, yeah.
So what we do in particular is focus on the Great Red Spot. And so that's the Great Red Spot now. This was taken by JunoCam, which is the camera on Juno. And the Great Red Spot is an anticyclone, which for those of us on Earth who are familiar with hurricanes, we'll do some comparisons to a hurricane. So people, what their closest analogy is a hurricane, but it's actually the opposite in a lot of ways. So hurricanes are cyclones, which means they rotate in the northern hemisphere counterclockwise. And they're low pressure systems that have very strong winds in a central eye. So hurricane forecasters always tell you to, look at the eye wall. That's where the strongest winds are. The Great Red Spot, it's the opposite. So it rotates counterclockwise, but it's in the southern hemisphere. So if it was in the northern hemisphere, it'd be the opposite. Its strongest winds are in an outer region, an outer ring around the planet, or around the storm, I should say. And it's a high pressure system. So it's the opposite of a hurricane in most respects, but it is a rotating storm. So in that sense, you can think of it in a similar context. And so we have some good observations of the red spot. This is, I wanted to highlight this because this is really new. On Juno, there is an instrument that measures emissions from emissions at different wavelengths of radiation corresponding to different vertical levels. And so you can see in this diagram, the Great Red Spot here in the cloud tops, and then you can see a signature of the Great Red Spot, and it gets progressively weaker as you get further down into the planet. So it is not that deep. They constrained the depth in this study to less than 500 kilometers, which sounds like a lot, but the red spot is 15,000 kilometers across. So it is comparable to, I believe I calculated it yesterday, 9 to 10 sheets of paper thin. So it's a pretty thin feature, but of course on Earth, very thin features, vertical motion is incredibly important. So we can't consider it just to be a flat pancake, but it is fairly shallow, all things considered. It is deeper than we might have thought, though. So that was a pretty interesting study that came out just in the last couple of years. But the main thing, one of the big things we don't know about the red spot and kind of the motivation for what we do is this. So the red spot in 1879 looked like that. And then this is what it looked like in 1974. This is from Pioneer 11. This is what it looks like in 2000. That was from Cassini. And then this is what it looks like in 2021 when Hubble took a picture of it. And you might notice this. It's getting smaller. And we don't really know why. So 150 years ago, it was about twice the size that it is now. And because we can, here's an Earth for scale. So that is from the late 1900s in the Voyager days. That is what Earth would have looked like next to the red spot. And then this is from just a couple of years ago. So no worries, Earth is not falling into the red spot. But that's what it would look like if it did. And so this is an interesting question, right? We don't know why it's shrinking, but it is. And this has been well characterized, and there's some interesting dynamical changes that are going on and some things that are staying the same. But so this is kind of why we started this project. We wanted to figure out why the red spot's getting smaller. And so now Gary will talk a little bit about some possible ideas.
Okay, so let's see. Okay, yeah, so on Earth, which is where my expertise mostly resides, we know that one of the things that can lead to long-lived high-pressure systems is interactions with smaller weather systems. And so this diagram here kind of shows a long-lived blocking pattern with smaller weather systems coming in and interacting with it. And many studies have shown in atmospheric dynamics literature that this maintains and can reinforce that weather system and allow it to become long-lived. So that's one mechanism. Another mechanism on Earth is that condensation releases heat, a lot of heat. And so when you have small-scale storms to the west of a large anticyclone, the red on this diagram shows heating from smaller storms. And then the kind of anticyclonic rotation area is indicated there. But when you get water vapor phase changes, that can add heat that then also prolongs the storm. And so there's two mechanisms that we thought, well, these happen on Earth. Do they work to help maintain or perhaps control the size of the red spot? During the Pacific Northwest heat wave of 2021, there was a great example of this where you could see heating upstream and then this sort of rolled up anticyclonic circulation that developed and produced this deadly heat wave in the Pacific Northwest, Western Canada. And that was an example where without the heating, that event didn't happen. And so perhaps some of these mechanisms are at work in maintaining or controlling the size of the Great Red Spot. So there's other mechanisms too, but these are two that we thought about pursuing. And one way that we can check these mechanisms is using time-lapse photography. And so this first image here, this Pioneer or Voyager? Voyager. As Voyager was approaching Jupiter initially, you could do a time lapse and take one image per day. And what you see, if you look at this, is these smaller scale disturbances are racing along, and some of them are getting ingested into the circulation of the Great Red Spot. So that's compelling evidence along the lines of what we know from the earthly literature. And we have some of these other time lapses from various other missions that show kind of what we were looking for, where you can see these smaller disturbances becoming incorporated, wrapping into a larger disturbance and as they shear out. So that gives us some ideas, a couple of hypotheses that we could test, because we do have enough evidence that these type of interactions are happening, or at least that they were. Perhaps if they're happening less frequently now, that might be one explanation for why the storm is reducing in size. We also know that as the storm gets smaller, it's going to tend to move more with flow. That might reduce the level of interaction. So there could be a feedback there. And so these were some of the hypotheses that Caleb and I developed in our weekly meetings. We would kind of alternate between frustration with the computer model and talking about the science of the red spot. And so we had a couple of hypotheses, and we'd love to be able to test these hypotheses. And so that's where the next step comes in.
Yeah, so Gary mentioned it briefly. So what we want to do is we want to take some of this theory and we want to test it in a simulated environment. And what we mean by that is we want to take theoretical meteorology, so atmospheric dynamics, equations that describe how the atmosphere changes over time, and implement them in the form of a computer model. This step was already done for us. This is a model, it's called the EPIC model, the explicit planetary isentropic coordinate model. And this was developed in the late 1990s and early 2000s by Tim Dowling and his friends and some very smart people. And what we want to do is we want to take this model and all these observations that we've been talking about, all the satellite data, all of the amateur astronomer observations, and we want to replicate the Great Red Spot inside of this laboratory. The idea being, if we can do that, if we can get a storm that looks like the Great Red Spot and simulate some of its behavior, then we can tweak some of those parameters and we can test things like interactions with smaller storms to replicate this shrinking. So that's the pipeline of what we want to do. And we have made some significant, if slow, somewhat slow progress. So we got this model. This model is publicly available through NASA's planetary data system. And so we downloaded it, we opened it up, and we put in a what we hoped would be a Great Red Spot. And this is what we got. So this is not exactly what we were looking for. This is it's a spot, but it's not great. So then we decided to write our own code in attempts to make it a little bit better. And this is what that looked like. So also not ideal. So then we got in touch with the developers of Epic, and they sent us their latest version of the model that they're still developing. And this is what happened when we opened that one up. So still not great, but we were persistent. And over time, we started getting things that looked a little bit better. And then by the end of the spring, this is what we had. So this took about a year or a little over a year for us to get from this point to that point. But we're here now. And so starting this semester, we have been able to do some really cool simulations. And this is where we are now. So I put everything up all at once so you can kind of look around and see some of the different observations that we have as I'm talking. But over here, this is a comparison of the actual Great Red Spot as seen by JunoCam in 2020, and then our model Great Red Spot. So you can see it's a little bit smaller, but it replicates a lot of the structure and the motion of the Great Red Spot. It rotates counterclockwise. Its strongest winds are in an outer ring around the center of the storm. It moves to the west, like the Great Red Spot does. And so this is a cool 90-day simulation. The fact that it's 90 days makes me very happy because for a while we couldn't get a spot to last more than 12 hours. But 90 days is pretty great. And so it's drifting to the west more quickly than the actual red spot is. And its winds are too strong. So you can see in this diagram, the winds are in the right place, but our fastest winds are twice as fast as the actual fastest winds. So it's rotating too quickly and it's drifting too fast and it's too small. All of these differences are actually consistent with each other meteorologically. If we were able to get a bigger spot, it would rotate less quickly and it would drift more like, hopefully more like the actual red spot does. And then this is a diagram of the rotational structure of the storm. So we can see a couple of things like this is a published diagram from last year where you can see there's these purple spots here to the north, particularly the northeast and the northwest, and then to the south. And we get some of that structure here around the spot with these purple patches that almost like, it looks like they hold the spot together. And then that's a 3D visualization over here. And so the red material, the red surfaces anyway, correspond to the spot and the things that the spot creates. So there's some pieces that separate themselves at the beginning that eventually interacts later on with the red spot, which is actually how, so far, that's our best indication of interactions with smaller weather systems. So you can see here when this comes back around, when it starts, there will be a little piece that comes off of it at the beginning. I think it's, which piece is it? This one. Watch this one. It gets pulled in to the bigger storm as it passes by. And you can also see that in this simulation where this is a plan view, where there will be these little vortices that get pulled off of it at the beginning. So like this one, and then they get sucked in like a vacuum as the simulation goes on. And so one of the things we want to do this with the rest of this year is look at these interactions more closely and see if they are having a sustaining effect, and to do this intentionally by putting in smaller storms that the red spot can absorb, and see if that impacts its size or its longevity. So right now, this spot lasts about 360 Jupiter days, which on Earth is like 4 months, which is not anywhere close to the at least 150 years that we're shooting for. But it's pretty good. And so it turns out that this is really hard to do. It took us a long time to get to this point. And we've successfully replicated a lot of what we actually see in the red spot, if not perfectly. We've simulated its drift, we've simulated its rotation. Again, not to perfection, but at least in general, we have done that in a Jupiter-like atmosphere. And so that's a really hard thing to do. But we've managed to do it thanks to all the people who developed this model, and to all the really great observations we have from the past 100 years or so with all the spacecraft and the amateur astronomers who do their observations. So this has been a really cool project and a really excellent learning experience for me, at least. My first experience with numerical modeling and the challenges that come along with it, but it has been it's been really fun. So these are all the people that supported me in this project. So Raul Morales Uvarias is a scientist from New Mexico who works a lot with EPIC, and then Tim Dowling developed EPIC. So he's going to be, those two in particular have been big resources for us as far as EPIC goes. And then Ramana Sankar and Sean Bruthdaber are also EPIC users in the community who've helped us. Dr. Ayer, who is a professor here in the meteorology department, who is my dynamics professor, was a great sounding board. As I was learning dynamics, I would go up to him at the end of class and say, okay, so how does this apply to the red spot? And he would give, we would chat a little bit about it, and that was really helpful. Lisa Lowe at the High Performance Computing Services here at State helped us compile EPIC and get it running. And then NASA and the North Carolina Space Grant fund this research, and the Goldwater Scholarship and Astronaut Scholarship foundations have supported me in going to school. And Lenovo is the corporate sponsor of the Astronaut Scholarship here at State. So I wanted to give them a shout out too. And then this image is representative to me of citizen scientists, because this here is this white spot here, that's Clyde's spot. And Clyde is a citizen scientist from South Africa, Clyde Foster, and he discovered this spot. It formed in the last several years, and he saw it with his telescope in South Africa, and he contacted our friends at JPL and said, hey, point GenoCam at this place and see what it is. And it was this spot. And so it got named after him, Clyde Spot. And there's tons of stories like that in the Jupiter science world. We wouldn't be able to do any of this without citizen scientists. They are really they keep this, the fuel that keeps this work going. So big shout out to them as well. And these are all of our sources and where all the images came from. So thank you.
Thank you both so much for just a fascinating talk. We do have time for question and answer. So if you do have a question, put your hand up and my colleague Hannah will bring the mic over to you.
This may be a trivial point, but on the Juno orbit that you were showing, it was smooth, smooth, smooth until it got to the planet, and then it zigzag, zigzag.
Yeah.
And I'm just wondering why that isn't also smooth.
Yeah, so the actual orbit is smooth. It doesn't do those zigzags. That is, I believe, an artifact of in the data that OpenSpace uses. It's moving so fast at that point that it only actually catches so many points, and so it catches like 6 points as it goes around the planet, and then it just connects them with a sharp line. So it's unfortunate. I wish they would get it a little bit better, but it's hard to do in data visualization sometimes. So that's why it looked like that. But
my watch does that if I run too fast.
Hi, Caleb.
Hi.
I was just thinking about while you're talking, so when it sucks in the vortices, does that in theory make the spot move faster because it's absorbing more energy, or would it make it go slower because that might be making it bigger?
that is a good question that I would have to think about a lot.
Okay, sorry.
No, that's great. These are the kinds of things that we've been talking about, like what would make it rotate more slowly and what would affect its size. So that is something that we'll be thinking about, and we can chat about that sometime.
Yeah, okay,
Yeah.
good to know, not the only one.
Yeah,
So that's the beauty of having a numerical model. I mean, we know from the theory kind of how that works from the papers from the 1980s, and so we know the equations in the theory. But with the model, you can actually measure the energy budget of the storm, and you can measure it before and after these vortex interactions and see how the potential and kinetic energy changes and how the size of the storm changes. So with a computer model, you have, even though it's imperfect, but you have observations of every quantity you need in every location at every time. You just hope that it's faithfully replicating what's happening in the real planet. And I also just wanted to point out with Caleb's work here, it may not be evident from what he showed, but to take a computer model and run it in a high performance computing environment and a distributed memory computer is not something that undergraduate students typically do. And Caleb is sort of operating at a graduate student level with this project. And I think we've all learned a lot about the EPIC model, which I had never used before. We're grateful to Jim Dowling for making it available. But the fact that we've got storms that can live longer than a week in this model is a kind of remarkable accomplishment, because there's probably mechanisms happening on Jupiter to keep the great red spot going that aren't in our model. But I think now we have some testable hypotheses, and my hope is that we can get a journal paper. It would be even more rare for an undergraduate research project to result in a journal paper. So that's our hope if things go well for the rest of the year. But Caleb, when I'm working with grad or undergrad students and you start working with numerical models, it's really easy to get frustrated because they don't compile or they produce crazy output. I actually encourage Jake to put the bad results up here because that's part of the process. And the part of the process of becoming a responsible scientist using numerical models is recognizing what bad output looks like, why it's bad, and how to fix it. So I think there's a lot of learning that happened in that process, and that's why it's important to share those bad results as well. But it's a really impressive accomplishment, because when it would work well, we'd meet every week and he would come back and he would say, I did 10 more simulations, and I tried, and I would bombard him with things to try, and we would think about, okay, well, why is this behavior happening? What are the different possible causes? Let's explore them. And he never gave up. He never got frustrated. He just kept persevering. And I said, this guy's going to be a great graduate student someday, because everyone gets frustrated and wants to quit when the model isn't working well. So I just wanted to throw that out there, that it's harder than it looks.
Thanks. So in the photographs you showed in the 1870s to the 1970s, the storm shrunk a little bit, and then over the next 50 years, it shrunk a lot.
Yeah.
So
So
is there potential there's not 150 years model left? Like, is it going to disappear?
So we don't really know what the future holds for it. You're right that it shrunk a little bit and then has since shrunk faster. So it is accelerating. But the thing that is interesting is it's visibly shrinking, but some of its like its rotation has not shrunk. So the storm itself has not weakened per se. It is just covering a smaller area. And so in one sense, yes, it is disappearing, but in another sense, it hasn't really some of the like strength parameters that we might think about in terms of, you know, how long it's going to live haven't changed all that much. So it's an open question. We don't really know. So
There was one paper we read where it was interacting with some really strong vortices. Some people hypothesized that it was about to die, and they thought the vortices might break it up.
let's see.
But that didn't happen. On the contrary, it increased its strength after that.
Yeah, you can see this in this image, this red material being pulled off by this gray spot. This is from that paper. So it pulled off these streamers. And so they published a paper about it where they did some simulations of it. And so it didn't, it affected the size, but not the strength. So pretty interesting.
So I know that a lot of your work has been focused on the Great Red Spot specifically, but with that shrinking, do you know, has there been any indication of like other changes in Jupiter's atmosphere, like anything growing or other things shrinking or anything like that?
Yeah, so there's plenty of stuff. Like Jupiter is one of the most visually dynamic planets. Stuff changes on it all the time, which is part of why I like it, because as a meteorologist, to be able to see with the colors and everything, all the motion that's changing, it's pretty cool to think about. So there have been other storms that have developed, like Oval BA, for example, in 2003, smaller storms merged into one big storm, and then it turned red, and then it turned white again. And so some of that stuff happens all the time, and there's haze everywhere. Sometimes the bands disappear, like sometimes there's material that covers some of the darker bands, so then those just like don't look like they're there anymore. So stuff changes all the time. Whether it's related or not to the Great Red Spot, I don't know. But more observations of like the deep, like the interior and what processes force the things that happen in the cloud tops would be needed to actually make that connection. But yeah.
I have one more question. Back here, but you're next.
I know most of your like research focuses on the decay of the Great Red Spot, but are there any proposed like hypotheses for how it like developed initially?
Yeah, that's we've talked about that some where when Gary was reading about it like a while ago, this theory that some huge like meteor flew into Jupiter and lodged, and then this disturbance, semi-permanent disturbance formed. That I don't think there's been much work into that recently, but that was a theory a while back. And then there's some stuff about like how vortices form and instability, but nothing. That's another question, like how did it form, and then why does it live so long? In addition to why it's getting smaller, so you might have some more ideas about that. But
Yeah, and why is there only one? It's a great question, and we don't know the answer because it formed before we were observing. But we know from numerical model simulations that whenever we see these strong anticyclonic vortices develop on Jupiter, it's a convection print. When you have buoyant material from deeper in the atmosphere that rises up and hits a stable layer and spreads out. And that's what gives you that anticyclonic circulation. And so, and you can tell by the color that that's what's happening in the red spot, that there's material being lifted up. So we know there's some sort of a source of warmth underneath it. How that came about initially, there's various hypotheses, but that's outside of my expertise. And I don't think anyone knows for sure this competing hypothesis. but we know it's some sort of a buoyant convection current, and something is maintaining it, for all these hundreds of years.
And on the meteor point, there was a comet that flew into Jupiter about 30 years ago now, Shoemaker-Levy. And it created this disturbance in like this visible disturbance in Jupiter's atmosphere. And when I was interning at JPL, my mentor, he's been mentoring students for like 40 years. And when that happened, all of his students dropped their projects and worked on that because it was such an interesting thing to happen. So there's a lot of stuff like that that goes on. So not necessarily related to the red spot, but just cool.
This question might be a little bit silly, but so I was thinking, here or on any rocky planet, I think of weather as everything that happens between the rocks and up. So is this weather all the way down? Like, because it's like,
Yeah,
like, where does weather start and stop?
that's a great, actually, it's not silly at all. It's an incredibly interesting science question. So one of the big areas of research for Juno is the interior of the planet. And so we don't really know that there's potentially like a solid metallic hydrogen core. And then above that would be not surface, and not even like gas, but basically gas transitioning into just a more dense as it gets down, a high density fluid. And so the boundary between surface and atmosphere is very blurry, or surface between atmosphere and not atmosphere is very blurry. But at least for our purposes, in terms of thinking about the weather, there's no surface or interactions with another density fluid to be concerned about particularly. But there is a lot of work going on about like how deep this structure of the jet streams goes. That isn't known for sure. The red spot, we have pretty much constrained its depth to a certain layer, but so a lot of the like discrete features like the vortices are not particularly deep, but the jet streams we don't really know. So it's pretty interesting. I love thinking about that stuff.
Yeah, that is a great question. I think, we know the atmosphere is really thick, but we only are seeing the very top. We have a couple of probes and, Galileo dropped one, I guess, and then the Galileo, when it met its demise, they just crashed it into Jupiter to take a profile on the way down so that it wouldn't hit a moon and contaminate it or something. So we have only a few soundings. And so the only part that we can really study is the part that we have where we have at least a few observations. But what's happening deeper down, the numerical modeling studies show that you can't replicate the jets unless you account for the deeper convective motions in the atmosphere. So we know that it is affecting what we see, but the details are very much unknown.
Yeah.
Hi. So is this storm is becoming circular day by day? So,
Yeah.
so like in 1800, it was like elliptical, and now it's more like a spherical.
Yeah. So that's one of the things that's been noted about its shrinking. That's a great observation, actually. Here, it's very much an oval, and you can kind of see it. This is not perfectly to scale, but you can see it with this Microsoft PowerPoint oval, that the width of the spot shrinks much faster than the height. So yeah, it's getting more circular, and that's believed to be a more unstable configuration than the oval. I don't know the meteorology behind that, but I've read in some papers that that's a more unstable configuration.
We know from the theory that the smaller the storm, the more it will tend to move with the flow. And so when it was in this configuration, probably was able to ingest a lot more overtake or have smaller vortices interact with it. Now that it's smaller and more circular, that may limit its ability to interact with other disturbances. That's kind of one hypothesis for why it might be shrinking. It's just due over time, to reduce vortex interactions, but that's due to its shape and size that is what controls its movement. So I think that's that certainly plays into the ideas that will be, that I say we will be testing, that Caleb will be testing tomorrow.
Okay, thank you.
Hello. So you mentioned, so obviously this is not a perfectly two-dimensional storm, right? There's a thickness to it. Is the thickness also shrinking, or is the thickness approximately the same while the XY shrinks? Yeah, we don't know. Okay. The observations of the depth have come very recently. So that that's happy. So that's a happy accident. So this came 2021, and then there was another paper that came out in 2021 that used gravity to measure this. And they both constrained the depth to approximately the same region, but we don't know, we don't have observations dating back that far about its depth. So that's a great question. Okay. And I have one more question about when you're doing the modeling, it sort of appears that you're like creating the storm instead of just like popping it into existence, like popping the Great Red Spot as it exists now into the computer simulated environment. Is that true? Are you like making the conditions for the storm to develop, or are you like just putting the storm in the computer? That is a great question. So we start with a basic, like a base atmosphere that has no storms in it. And then we perturb that atmosphere in such a way that it's not exactly what the storm looks like. Ideally it is, but it's not perfect. And then from that perturbation, it develops into this thing. So basically we're putting in the storm, but there is some development that happens immediately at the beginning. Okay, so you're not like modeling what actually happened in creating the storm. You're just doing what you need to do for the storm to happen. Okay. Yeah.
And we've got time for one more question.
I have a question for Caleb. So you've talked about what you're doing this semester. What is beyond that for you, and what do you hope to, how do you hope to carry this research forward, and how will it impact your career?
Yeah, so this will continue until I hopefully graduate in the spring. And then I'll go to grad school. I don't know where yet or what I'll do there. Hopefully planetary science or atmospheric science, with focusing on planetary stuff. And I want to keep doing stuff like this and working on missions like Juno, and working with people who do that kind of stuff. A lot of people in the Jupiter world work on James Webb too. So that's another possibility. And I like the interface of the professionals and the citizen scientists. I like that those two communities collaborate very directly in a very productive way. So hopefully I'll keep getting to do stuff like that, but yeah.
All right, please join me one more time in thanking our speakers today. Thank you both so much again for an amazing talk, and thank you all for coming out. Please keep an eye out. We'll have more coffee and business later in the semester. Take care.